Okay, so let's jump into our last section here. I'm hoping I can do this all in one video. It's got a lot of stuff to it. Really, the culmination of everything we've talked about in this unit in terms of numerical data. So hopefully I won't have to do 2 videos, but maybe I will. I don't know. We'll see. All right, so we've already talked about the basics about SOCs. When you're asked to describe or compare 2 distributions, or just one, I want to see that shape, outlier, center, spread. I want to see all those things mentioned. I do not want to see just random numbers spit out with no context. Context is extremely important. You can do little bullet points. There's nothing wrong with doing bullet points for each part. But again, remember that we are analyzing real data. So we want to make sure that we're trying to make conclusions based off of that, or at least providing information based off of what we're given. All right, so what we're going to jump into today is specifically which measures of center and spread you should use. And that depends on the shape of the data as well as outliers. And we're also going to get into exactly how we know if a certain data point or data points are outliers in a distribution. So let's jump in. So for our measures of center, the most common are median and mean. Mode, we don't typically use for this class. It is technically a measure of center, but we don't really focus on mode very much. Okay, so the median is, if you remember, the exact halfway point with exactly half of the data values below and half of the data values above it. Your data points need to be put in order if you're doing this by hand. And it divides your histogram or your box plot or dot plot or stem plot or whatever into 2 equal areas. It has the same units as the data itself. And then your mean is the average of all of your data. Okay. So X bar would be the mean of X. So that's the notation. If you have a line over the variable that you're looking at, oftentimes we'll just refer to X bar as the mean of whatever we're talking about, but technically you could use any variable. So you should be comfortable with finding the mean at this point. Sum of all your data points divided by how many data points you have. And it also has the same units as the data. The mean is actually what's called the balancing point as well. So if your graph was made out of some sort of solid material, it would be the point at which the graph would perfectly balance if it was like resting on your hand or another object. And just as a side note, we normally use, like I mentioned, X with a line over it, X bar, to represent sample mean. And it doesn't matter which variable is used. You could have Y bar or A bar or whatever variable it is. But if we look at the Greek letter mu, okay, so that's pronounced mu, not like, the whatever it is that mewing actually is. Don't ask me about it, but not that kind of mew. But it refers to the population mean. It was a Greek letter first, all right? Stats folks had it first. So notice that there is different notation that we use for sample data versus population data. And that leads us to talk about what is actually a statistic. So like I said, we have different notation to differentiate where the data comes from. So a statistic is a number that describes a characteristic of a sample. A parameter is a number that describes a characteristic of a population. So notice they both start with the same letter, S for statistic, S for sample, P for parameter, P for population. So that's an easy way to remember it. But we use different notation for that. So X bar represents sample mean. That's a statistic. Mu represents population mean, and that is a parameter. So they are subtle differences, but they are extremely important. Especially when we get to second semester stuff, there is a huge difference in between X bar and mu. And we'll get to those later, like I mentioned. All right, so let's jump into finding some of our statistics in our calculator. So here are the directions for that. But if you look at the next example, the following data represents the number of writing utensils in a random sample of teachers' desks. Kind of a funny data set. Let's start by finding our mean and our median. We could definitely do those by hand, and with small data sets, you should be comfortable doing those by hand. But I do want to show you how to do these in your calculator as well, especially for larger data sets. So just like we did before, we're going to add a new document. We're going to select lists and spreadsheets. Again, add a new document every time and then either choose to save or not save your data. Because at a certain point, if you just keep adding documents, you're going to have like 15 documents and it's going to be really, really confusing. So if you just add a new document every single time, and again, either save or don't save, it doesn't matter. That'll make your life so much easier, trust me. All right, so go ahead, start entering the data here. So 1, 2, 4, etc., etc. I have mine saved, so I'm going to pull it up. All right, so once you have yours entered, you can name your list here. For these commands, you don't technically have to have your list named, but it's a good thing to get used to doing in case you do need it. For graphing, you definitely need the list named, but for this command, you don't. So from here, what we're going to do is we're going to press Menu, Statistics, Stat Calculations, One Variable Statistics. Don't change the number of lists, just press OK. And then you can use the drop-down menu to select your variable, or if you keep it as column A, that's what that means, it'll do the calculations for you. Either one's fine. Don't change anything else, just press OK. And here we go. Here's my X bar. The other numbers tell us other things too. We'll get to those later. And here's my median. And again, we could do those by hand. They're not really that difficult to do by hand. But this saves us some time because, like I keep saying, the context of the problem is way more important. All right, so let's write down our sample mean and sample median. So X bar, 16.095. I'm just going to say M for median is 10. And both of these are talking about utensils. So if you have a lot of statistics to list at the same time, I'm okay if you do bracket like that. If you have just one, don't forget to list whatever the units are that you're talking about or whatever objects it is, right? Okay, we're going to then graph the data on our calculator. Oh, I forgot to answer the follow-up question. So how are the mean and median different? So we notice that the mean X bar is greater than the median. So we're going to kind of go into that. So why is it that the mean and the median are different here? Okay, if they're both measures of center, shouldn't they both be at the center of the data? Okay, now let's get into graphing. So sorry, I had a bleh. All right, let's try that again. So the next thing that we want to do is we want to go to the home screen. We want to scroll down or use the cursor and then select the pink icon. That's how we graph. So this is where naming the list is important. You can't graph it on your calculator if you don't have the name of the list. Like I called mine example 1. You can call it X, Y, or Z or utensils or whatever you want to call it. Because you have to click to add your variable. And if you don't name your list, it won't record that as a variable in the document. So go ahead, click that. And it creates this beautiful little dot plot for us. And we can do this, I think we did this last lesson. If I asked you to graph on your paper, it's much easier to just do this by hand and set it in the calculator. But in the calculator, here, if I'm just saying, okay, graph it on the calculator, it helps us do it a little quicker, and then we can answer follow-up questions. So let's talk about the shape of this distribution and how do the mean and median show up in the shape of that data. Okay, so this distribution is definitely unimodal and skewed to the right. So the distribution of utensils is unimodal and skewed right. how do the mean and median show up in the shape of our data? Okay, so let's go to our graph here. Now the median is about 10, right over here in this closest cluster of numbers. And then the mean is right above that at about 16. So notice that if we were trying to say something about how many writing utensils teachers have in their desks, right? If we wanted to like go to Miss Howard and be like, they have too many things in their desks, or we wanted to say they don't have enough writing utensils, we need to give them more, or whatever it is. I don't know. But if we wanted to do that, we would probably want to present like a typical amount of writing utensils a teacher has. And so if we had to choose a typical amount choosing either between our mean and our median, because that's what really those are, that's what a measure of center is, we would probably want to choose the measure of center that's closer to the majority of the data. So we have several points up here, right? Teachers who have like 45 writing utensils in their desk. That's probably me, if I had to be honest. But if we wanted to say, okay, this is what most teachers would have, we probably would want to choose something closer to the majority of the data points. So we probably want to say around 10, maybe a few people have more than 10, but a typical teacher, the majority of the teachers have around 10 writing utensils in their desk. And then notice here that because if you think about the equation of the mean adds together every single data point and then divides by the total. So that's why the mean is pulled in this direction towards the skew of the data, towards these fewer, higher numbers of this distribution, because it takes into account every data point and the actual values of those data points, whereas the median just is simply the middle number, the exact middle. So that is why in this case, the mean is higher than the median, because it takes into account these larger numbers. Okay, so the mean is higher than the median because the mean, I'm just going to say X bar, is pulled in the direction of the skew. And again, that means those fewer, higher numbers have a larger effect on the mean. All right, very nice. Okay, so let's go ahead and keep experimenting with this idea of how our mean and our median are affected, both by the shape of the distribution, as well as what if we added another data point? What if we added a point that's 99 utensils to the list and then found our mean and median again? Okay, then we're going to see how did they change and why we think this is. So let's just use our cursor, go back to our list here, and then let's scroll all the way down and then add 99. Now, the nice thing with the Inspires is they'll automatically recalculate everything for you. So if you press Control 7, it takes you right back to the top of the list. Then we can see our new mean, 19.863. And if we scroll down, see our new median, 10.5. Okay, so after adding 99 Luftballons, no, just kidding, utensils, I'm just going to say abbreviate that, we see X bar is 19.864 and median is 10.5. Oh, again, I got to put my units here. Okay, so notice that if I'm looking at the difference in between the original mean and median and what they are now, notice that the mean increased by about 3 units, almost 4, and the median increased by only about 1 unit, or half a unit. And so notice that adding this one point here, which if we look at our graph and zoom out, so again, menu, window, zoom data, this is very clearly an outlier. Okay, this is an unusual point. So if we add in an unusual point, our mean tends to be pulled in that direction even further than it was from the skew, pulled in the direction of that unusual point. So we see it, and this shows that the mean is pulled, or I'll say more affected by this outlier at 99 utensils compared to the median. Which makes total sense. Again, if you think of what we do when we find the mean, find the average, it's going to take that one value into account way more than the median. All right, so what do we think would better represent the data without the 99? So for example, this is going back to what I said earlier. If you could only report one number to describe how many writing utensils are on teachers' desks, which one would you choose and why? So I hope you see how the median is a better measure of center. Again, whether or not we include the 99 actually. So the median really tells us where most of the numbers are, and it ignores those few numbers that we see there. Okay, so the median, 10 utensils, would better describe a typical, we're not trying to focus on those few unusual points, typical number of writing utensils. Again, I'm just going to abbreviate that. Since it is closer to the majority of the data points. Okay, so very nice. So we are going to save this data set for a later example. So in your calculators, go ahead and press doc, file, and then either save or save as, either one. Take a second, do that right now. I'm not going to because I don't want to save the graph or the calculations, but go ahead and do that right now. Okay, all right, so the overall conclusion from what we just did. Okay, so our median considers only the order of the values, so therefore it is resistant to values that are extraordinarily large or extraordinarily small. So it simply notes that they are one of the big ones or small ones and ignores their distance from the center. In other words, okay, it always finds the number of the number in the middle, regardless of how big or small the first and last numbers are. So that's important, okay, because if we have a skewed graph, or if we have a graph that has outliers, we want to take into account the majority of those numbers and try to ignore the unusual ones. So when we're trying to choose between whether using the mean or median as our measure of center, we're going to start by looking at the shape of the data. If the graph is symmetric and there are no outliers, we can use the mean. That's still a really good measure of center. If the graph is skewed or has outliers or both, you're better off using your median as your measure of center. So that's really what I wanted to get at with this first example here. All right, so let's move on to our measures of spread. So you'll notice, especially with that last example, right, we don't just want to report like just that typical number. We would also want to talk about how spread out are the numbers, right, because they were very clearly not all clumped together. So it's important to mention if we have numbers that are very spread out, we want to talk about that too. And if they're not very spread out, we also want to talk about that. Think about, if you're when you're in your classes, and as a teacher, whenever I give an assessment, a test, a quiz, or anything like that, I want to look and see, did my students get about the same grade, right? If they got kind of close together to each other, that can or cannot be a good sign, right? It depends on the context of what we're studying and things like that. But that is one of the things that I look at as a teacher. I look at, are they generally close together? Are they really spread out? Because that tells me a lot about how the students understood the material and all that kind of stuff. Okay, so we're always going to report a measure of spread along with our measure of center when we're describing our distribution. That is the C part. C is the center. The second S is the measure of spread. Now, range is a real easy one. Range is just maximum number minus minimum number, but we only use it as a last resort. So say you only have a graph of the data, or you only have some summaries of the data that don't include the data points themselves, and you can't find other measures of spread that we're going to talk about, you can use your range, okay? But it has some problems. So let's get into that. So we're going to find the range of the data sets below. It represents a random sample of students who are asked how many countries they'd been to outside of the US. So if I'm looking at this data set, the range would be 10 minus 5. It would be 5 countries. Okay, that's fine. But let's say that one of the students accidentally wrote down 10 instead of 100, right? So the range of this data set, just changing that one number, now makes the range 95. So that's the problem, okay? We have similar data sets, but that one value, 100, changes the range to 95, which is not indicative of how spread out the numbers are. You have this one person who went to 100 countries. Most other people went to like maybe 7 or 8 countries, right? Okay, where the range would be 4 countries typically, okay? And that's a problem, okay? So that's why range is a last resort kind of thing. Okay, so we only use it if we can't use other measures of variation. So one of the main ones that we're going to use involves what are called your quartiles. So quartiles are measures of location, or denoted Q1, Q2, and Q3, and they divide the data set into groups of about 25% in each group. So the first quartile separates the bottom 25% from the top 75%. Second quartile, which is the same as your median, separates the bottom 50% from the top 50%. Third quartile separates the bottom 75% from the top 25%. And this is part of what's called your 5-number summary. Your minimum, your first quartile, also called Q1, your median, which is technically Q2, third quartile, which is called Q3, and your maximum. So that's our 5-number summary. So this really helps us break down the data in a nice, pretty, beautiful way. So we use the 5-number summary a lot, or we use pieces of it a lot. So let's take a look at our next example. This is a random sample of 11 high school students, and they were asked about how many close friends they have. And here's their responses. We're going to find the 5-number summary by hand. Okay. And like I mentioned before, the calculator does do a lot of the work for us. We don't want to let the calculator do the thinking for us, right? Because we want to make sure that we know what these numbers that the calculator are spitting out at us, what they actually represent. Okay, so when I'm doing my 5-number summary, I like to start with my median. So I'm going to list out min, Q1, median, Q3, maximum. Okay, I like to start with my median, although we can list out the minimum and the maximum. My units here are friends. So all of these are talking about friends. All right, so my median is my exact middle number. Since I have 11 numbers here, it's going to be the 6th number, right? 1, 2, 3, 4, 5, 6. Okay, I'm going to box that. Okay, so 3 friends. That's the median number of friends. Notice that about half the numbers are below and about half the numbers are above, not including the middle 3 itself, right? Okay. If I'm finding my Q1, I ignore that median that I just found and I find the middle of the first half of the data, which we can see here is 2. And my Q3 is the middle of the second half of the data, which I can see here is 4. Okay, and there's my beautiful 5-number summary. Now this one was nice because we have an odd number of friends, odd number of people we asked about their friends. But say, for example, I added one more data point to it. So say one person had 7 close friends. Okay, then when I'm finding my median, I would have to find the average of the middle 2 numbers. So with that, my median would be 3.5. Okay, then when I'm finding my Q1, I would find the middle number, which in this case would be the average in between 2 and 2. So my Q1 there would be 2, because 2 plus 2 divided by 2 is still 2. And then my Q3 would be the average in between these 2 numbers, so that would be 4.5. So adding one more data point can change it, but I hope you're noticing that it doesn't change it all that much from the original data set here, which is why, again, our median, which is one of our quartiles, is such a valuable measure of center because it is resistant towards other data points, even though 7 is not necessarily an outlier or anything. But even when we add one more data point, even if I added, say, 70, okay, I would still have those same 5-number summary that I just mentioned. But if somebody really said they have 70 close friends, I think they're lying. All right, very nice, very nice. So let's go on and let us graph some box plots. I love graphing box plots. They're so fun. So we could totally do this by hand. I guess we didn't really need to save that data set because we didn't enter anything in the calculators. But it's a good practice to know how to do it. So go ahead and go over to where it says current. So if you go down to current, it'll go back to whatever document you were on. And if you had already gone away from that document, remember you can go to browse and find that document again. All right, so let's go to current. We could graph a box plot based off of the 5-number summary, which notice our one variable statistics gives us that 5-number summary as well. So we don't have to always find that by hand, but it is important to be able to do that. So that's beautiful. I'm going to delete, I don't think I deleted that 99. If you didn't delete that 99, go ahead and delete that. I think that's what I said in my directions. Yeah, so we don't have 99 anymore. Okay. So when we graph a box plot, I'm going to start from scratch just so we can see how it looks again from scratch. We go to our home screen. Since we're graphing another graph, we press data and statistics. We click to add variable on the bottom. We select whatever variable we named it. So it gives us our dot plot again, but then we change the plot type just like we do for histograms. So menu, plot type, box plot. Now the advantage of doing a box plot on the calculator and then copying it from the calculator is that the calculator automatically does some calculations for you, which we're going to talk about in a minute, that have to do with determining whether or not data points are outliers. And they'll show up as dots. So if I go back to my list here and I add 99, and I go back to the box plot I just made and zoom out again. So Shira, if you're watching this in the future, you just walked in to grab a water bottle. But anyways, let's go back. Let's zoom out. Window zoom data. Okay, and it'll show up as dots like this. So if there are outliers, but here we are not using our 99. So let's go ahead, zoom back in. Okay, so box plots show the 5-number summary. So minimum, Q1, median, Q3, maximum. Now, just like when I told you to use the cursor to hover over a histogram, do not click on the box plot because it automatically changes the numbers. Don't ask me why. But this is the nice way of graphing in the 5-number summary. The box itself goes from Q1, shows median as a line and is somewhere in the box, and then Q3. And then the lines, what's called the whiskers, sometimes you've heard this called a box and whisker plot maybe. The lines extend oftentimes to the minimum and the maximum, but if you have an outlier, they'll extend to the next lowest number. So again, if I add that 99 back in and I go back here, 99 would technically be my maximum, and the next lowest number would be the end of the whisker. All right, so please use a ruler on this, just like with the histograms. So you choose a scale. You always graph this on graph paper. You choose a scale that's reasonable. You can use the one that the calculator suggests. Like here, it's going by 5s, which I think is totally reasonable. So yeah, let's just go ahead, graph our number line. There's no vertical axis with box plots, just a horizontal axis. So this one starts, let's go 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and always label what your variable is, number of writing utensils. All right, and then your box plot doesn't have to be necessarily a certain width or height, but you do want to use the numbers here, your 5-number summary, to graph approximately where each of the endpoints and lines go. So I'm going to start with 1. My Q1 is 6. So I approximate somewhere up here. That's about 1. And then 6 would be maybe here. And I'm going to use 3 boxes for the height of my box plot there. But I could technically use like 4 or more if I wanted to make it nice and even, which that would be nice. Oh, it didn't. Okay. And that's fine. I'm going to shift this down here. You don't have to have that little hash mark at the end if you don't want to, which I'm going to erase. Median is 10. Q3 is 30. Maximum is 45. So 10, 30. And then maximum is 45. And we make our beautiful box plot, which is why I use a ruler. All right, and there we go. That's our beautiful box plot. So let's talk about the shape of our box plot. So we can still describe the shape of the box plot. The problem is you can't see modes, so you don't technically know unless you look back at a dot plot or something, whether it's unimodal or bimodal or whatever. So you just want to say whether it's symmetric or skewed. So use the length of the tails as well as where the median is positioned to find the shape, okay? Because notice that this tail is much smaller than it goes. Here's probably where the peak is, since that's where the median is. Then it goes down on this way. So this is very clearly skewed right. Okay, which we saw last time when we graphed our dot plot, right? Okay, but again, with the box plot, if we're thinking about what we can say just based off of the box plot, we only know it's skewed right. We can't say a mode. Okay, and what's called a modified box plot is what shows you outliers. So we're always going to do modified box plots in this class, but it'll only ever ask, like I said, modified box plot here. Your homework or test or quiz may or may not specify that it's a modified box plot. If it just asks for a box plot, always graph modified box plot, meaning if there's outliers, do that. But we already added 99 back a million times, so I don't want to do that again. Okay, so there's our cute little box plot there. Now our box plot and our 5-number summary also gives us another measure of spread called the interquartile range, IQR for short. And one of the nice things about the interquartile range, IQR, is it ignores extreme data values and concentrates on the middle of the data, okay? So the equation for our IQR is upper quartile minus lower quartile, or Q3 minus Q1. That is why it is called the inner quartile range. It takes the middle two quartiles, because Q3 is the 75th percentile, so has 75% of the data points below. Q1 is the 25th percentile, and so it finds the range for the middle 50% of our data, which is beautiful. All right, so let's find our IQR for this data set. So we can go back to the list itself, or just look at our box plot. Q3 is 30, Q1 6. So the IQR here is 24 utensils. Okay. Now, the IQR allows us to see that range for that middle 50% of the data, which is super nice, right? Because then it also takes into account, if we're looking at the context of this problem, right? We want to say, here's our typical number of writing utensils. Here is how spread out the middle half of the data is, which, if you remember how the dot plot looked like, that was super important, right? Because it wasn't just that one clump of teachers that we had on the left-hand side. We had a fair amount on the right-hand side too. So we don't want to just say, oh, it's 10 utensils done. No, we want to say basically they're spread out by about 24 utensils, which is a lot. That's a lot of variation in how many writing utensils each teacher had in their desk. And it also gives us how to find outliers by hand, which I mentioned the box plot in the calculator does for us, but we should be able to do this by hand, and these are some equations that you need to memorize. So if you have any data points that are below, not equal to, but below Q1 minus 1.5 times the IQR, those are outliers. Or if they're above, not equal to, but above Q3 plus 1.5 times the IQR, those are outliers. So let's think about these equations and think about where these equations would come from. Okay, why would these equations quantify our outliers, and what are outliers equations finding? So basically we're saying is if we have a data point that's 1.5 times the IQR below Q1, or 1.5 times the IQR above Q3, those are so far away from that middle 50% of our data, those are super far away, that those would be considered outliers. So if the data points are 1.5 times IQR above Q3 or below Q1, they would be outliers. And again, why is that important? Okay, that's really far away. That is really far away from the rest of the data. So that's why those would be considered unusual points. That would be outliers. All right, and I already mentioned this. Calculators already find outliers for you. Okay, another measure of spread called our standard deviation. Okay, so all of this, again, all these little detail-y things here is to get to describing distributions in a thorough, meaningful way. Okay, so using our SOX shape, outlier, center, spread in a thorough, meaningful way. All right, so some people say that standard deviation is more powerful than IQR, okay, because it takes into account how far each data point is from its mean. So when I say deviation, I'm talking about the distance of a single data value from its mean. And if you were to find all of the deviations of every single data point and add them all together, that would always give you 0, which comes back to that idea that the mean is your balancing point. So I love stats because it's like, and I love math in general because it's super cool. Like, how would you, every single time you find those deviations, you take each point and subtract its mean and then add all those deviations together. It's going to give you 0 every time. It's so cool. Now, what statisticians did, because basically what they were trying to do is they're trying to say, okay, standard deviation. What we're trying to say is, on average, how far away is each data point from its mean? That's what standard deviation is talking about. So they were like, okay, let's find those deviations. And then every time they added them together and they got 0. And then, well, that can't be true, because if the deviation of all of our values were 0, that would mean that each data point had to be exactly the same, right? So what they did is they did a little math magic. Instead of finding the average difference, they find the average squared difference. So you'll notice in our equation down here, okay, this is called the variance, this equation as it's listed, is found by adding together the squared deviation. So notice that's where we see x minus x bar, each data point x minus its mean x bar, squared. And then what they did is they divided by technically n minus 1. And this has to do with a lot of theoretical things about finding what is called an unbiased estimator, which if we want to get into that, feel free to get into it on your own. I'm not going to get into it in this class. It's definitely one of those things that if you continue your math career, you'll get into that in more detail. But they basically averaged it is basically what they did. Okay, now this is technically what's called the variance, which sounds a lot like variability. But they wanted the standard deviation, the average distance from the mean. So to undo squaring everything earlier, they took the square root of that final answer. So your standard deviation S is your square root of your variance, and also using the same units. So like I keep saying, standard deviation is the average distance of each observation from its mean. That's the mathematical definition, even though they're doing some magic here. All right, so let's jump into that. So what we're going to do is we are going to find the standard deviation by hand to give us a better idea of what it is, okay? But we're going to do it with a very small data set, okay? This is the data from example 2. And again, this is a random sample of students who were asked how many countries you've been to outside the US. So the first thing that we need to do is we need to actually find the mean. So remember x bar, if we did that by hand, we add them all together, 5 plus 7 plus 7 plus 8 plus 9 plus 9 plus 100 divided by 1, 2, 3, 4, 5, 6, 7 students. And that gives us 20.714 countries. Okay, so on average, we're saying that they visit about 20 countries, which again, remember that 100 there. Okay, that's going to come into play a lot later because it doesn't look like that's like a typical amount for this situation. All right, so to find the standard deviation, okay, so standard deviation equation, square root of x minus x bar squared, the sum of all those deviations over n minus 1. And n is just the number of data points. Okay, so we're going to take each number, subtract its mean, and then square that. So I'm going to take 5 minus 20.714 squared. And then I'm going to add that to 7 minus 21.714 squared. And then do that again. 7 minus 20.714 squared. And 8 minus 20.714 squared, 9 minus 4 squared, keep going. Oops. Okay, So I'm going to do all of that, okay, in the calculator. All right. Once I do that, I get about 7,345.42. So that's the sum of all the squared deviations. And then I'm going to divide that by, there's 7 total data points, so divided by 6, and then I'm going to square root that. And that's going to give me 34.989 countries. Okay, so the reason I wanted to do this once by hand is so that you know really what the standard deviation is all about. We take each individual data point, we subtract its mean, we square it, add all of those together, and then divide by number of data points minus 1, square root that, bam, we got standard deviation. Just like before, we're going to have our calculators do that work for us most of the time, okay? So I'm going to show you how to do that again right now. But if you think about what the equation is telling you, again, average distance from the mean, that's pretty powerful. It is a very powerful measure of spread. Okay, so let's go to our calculators. Go ahead, select a new document. I don't want to save this because I've got the original data saved. Go ahead, enter the numbers here. So 5, 7, 7, 8, 9, 9, 100. And then we're going to do a one variable statistics. So again, you don't have to name the list for these ones. Menu, statistics, stat calculations, one variable statistics. And just as a side note, part of what I will test you on our first unit test is that like you can do all the calculator commands also. So practice those. All right, so we've got our mean right here. Right down here, that's our standard deviation. So always use SX. You'll notice below it, it has what's called sigma X. Don't giggle. But that's another thing we're going to get to later, but always use SX for our standard deviation here. All right, so let's practice interpreting our standard deviation, explaining what it tells us about our data. So what we're saying is we're saying the average difference or deviation in number of countries visited from their mean of 20.714 countries is 34.989 countries. Okay. So this is one possible measure of spread, measure of variation. Okay. Another one that we did earlier is our IQR. Let's find our IQR, which since we just entered the data in our calculators, we can do pretty quickly. So if we scroll down, we can see here's my Q3, here's my Q1. So the difference in those is 2. So the IQR is 2 countries. How are the IQR and standard deviation different? Well, the standard deviation is a lot larger. Why is that? Well, that's that pesky 100 countries that somebody is probably lying about, but whatever. So again, because the standard deviation is an average, it takes into account those really large or really small numbers, those possible outliers. Actually, the 100 is definitely an outlier, okay? So it is not a resistant statistic. The IQR is a resistant statistic. It is not as affected by those values. Same thing with skew. Standard deviation is also affected by skew. Okay, so it's a powerful tool, but it's not powerful if the data isn't nice and symmetric without any outliers. Okay, so how are the IQR and standard deviation different? The IQR is a lot smaller than the, I'm just going to say S for standard deviation. Why do we think that is? This is because 100 countries is an outlier and standard deviation is affected by outliers. In this case, increases, or it increased the standard deviation by a lot. So if we were describing this distribution, we would definitely want to say the IQR, the measure of spread that we would use is 2 rather than 34, almost 35. Because we would want to mention that there's definitely an outlier. That's part of SOX, right? Shape, outlier, center, spread. Okay. And when we're mentioning our measure of center, we don't want it to be as affected by those outliers. So that's why we would probably want to say the variation in the amount of countries people have visited is probably about 2 versus 35, because that's really way too big for most of the data. Okay, so let's take a look at the next one. So we're going to delete the number 100 and see how everything changes. So notice it changes automatically. So if we find our IQR again, hey, look, it's still 2, okay? How have those statistics changed? So IQR is 2 countries. Standard deviation, if I scroll up here, look how much smaller that is, 1.517. Oh my gosh. Standard deviation, 1.17. Again, okay, the IQR didn't change, but standard deviation changed a lot. So it was reduced by more than 30 countries. Again, why do you think that is? IQR is not as affected by outliers. Sometimes it is a little affected, but it's not as affected. Okay. Which would be a better representation of the data if 100 was kept or not? IQR, because it does not take into account that extreme value and better represents how spread out the rest of the data is, which is what we want. Okay, so I know these ones have been kind of saying the same thing over and over, but I'm hoping you're really getting what I'm saying here. Okay, so different scenario. Let's say instead we added 5 to all the data points. Let's think about how our IQR and our standard deviation would change. So let's look at a graph of the data. So let's say we add 100 back in. Okay, let's look at the graph of the data. Oh, I need to name my list. Let's just call it C for countries. Okay. So most of the data is over here. Here's 100 way over there. Okay, so if I added 5 to every single data point, okay, everything would shift up 5, including the 100. It would now be 105. Okay, so how would that change how spread out the numbers are? It wouldn't, right? Everything would just shift up 5. It wouldn't change the spread, which IQR and standard deviation are. Okay, so the IQR and standard deviation, you could say S there too, would not change. How about the mean and the median though? if I added 5 to everything else, or everything, how would mean and median change? Those would be increased by 5. Okay, but mean, x bar, and median would both increase by 5. So that's kind of fun, okay? If you rescale the data, if you shift it in this case, okay, then it is going to change some numbers, some statistics, but not all of them. Okay, so overall, let's put it all together, all the things we've talked about with our socks, okay? Again, when I'm asking you to describe or compare distributions, always include these, okay? And do it just like I've talked about in the notes so far. We're going to do a couple more examples to really put it all together. But make sure you're being specific, make sure you're being detailed, make sure that you're including context and using your brain. All right, so when we describe the center with mean, we should use the standard deviation as our measure of spread. Those should go together. And on the other side, when we describe the center with our median, we should use our IQR as our measure of spread. So when should you use those? Okay. If your data is symmetric with no outliers, remember how I had said earlier, that's when we're going to use our mean as our measure of center. Okay. So looking back over here. If the graph is symmetric, no outliers, you're going to use the mean, which means you're also going to be using your standard deviation. If it is skewed or has outliers or both, you're going to use the median. So that means you're also going to use the IQR. Okay. All right, now say you're comparing 2 or more distributions with different shapes, okay? Or if one has outliers and the other or others don't. You're just going to refer to your median and IQR if that's the case. If one's symmetric, the other's skewed, use median and IQR. If one has outliers, the other doesn't, use median and IQR, okay? Because like we've shown over and over, those are resistant statistics, okay? Those are more reliable with those outliers or with those skew, okay? Always use your context of your problem and always ask yourself, what is the bigger picture? I do not want to see just a bunch of numbers and words that don't make sense, right? So think about what are we saying? What's the bigger idea, okay? All right, so let's do a couple bigger questions. I love this kind of stuff. This is so fun. Okay, so there's probably some baseball fans out there, okay? So, and you may or may not be a Dodgers fan. I don't know. My family is split. My spouse grew up in the Bay Area, and so their family is Giants fan, super big Giants fan. My mother-in-law, and my sister, her daughter, both of them, like, anytime I wear any kind of Dodgers gear, they like freak out at me. I am not like a huge fan, but I love going to games. I pay attention sometimes. But I find it fun. I don't watch on TV because that part to me gets boring, but I love going to games, and I've lived in LA my whole life pretty much. So I'm by default basically a Dodgers fan. But anyways, so let's jump into this example. So you may have heard people arguing a lot about how much players earn, okay, how much teams pay their players, okay? Is there a significant difference between those teams and what they pay, right? Is the saying true, you get what you pay for? Specifically, we're going to talk about Dodgers versus Giants. And this is the team salaries in millions for 2 teams in the 2023 season. So you'll notice below, I've also given you number of wins, losses for both teams and their winning percentage. Okay, so for the Dodgers, you can see winning percentage is a lot more, blah, blah. Oh my God, a lot more than the Giants. So maybe I should send this video to my mother-in-law. I don't know. And then below, we have their team roster with how much each player made in millions of dollars. Okay, so the first thing we're going to do, it's going to take a few minutes. I know it's going to take time. I know it's going to be tedious, but practice, okay? And we're going to enter the data into two separate columns in our calculators. So we're going to put all of the Dodgers into one column, and then next to it, we're going to put all of the Giants into another column. And there aren't the same number of players on each team. So again, go to the home screen, select new document, add lists and spreadsheets, all Dodgers in column A, all Giants in column B. Okay, I'm going to find mine because I already did it, so I don't want to, I don't want to have to do it again because it is tedious, but it's good to practice. Okay. All right, so it'll look like this. Definitely name your lists. You don't have to go Dodgers and Giants. You can say D and G or whatever. But there are 27 Dodgers. There's 28 Giants. Okay, so pause the video. Go ahead and do that. Okay, so then we're going to draw what are called side-by-side box plots of the data in our calculator. Okay, and we're then going to compare the two team salaries and answer the question, what can we say about the phrase, you get what you pay for? Okay, so on the next page, here's our graph. When we're drawing side-by-side box plots, again, make sure that both of your lists are named, okay, whatever you want to name them. Go to the home screen, select the pink icon, click to add variable, click one of them. It doesn't matter which one you click first. I'm going to go with Dodgers first. Change the plot type to a box plot. So menu, plot type, box plot. Okay, we got 3 outliers up here, which is not surprising, right? All right, so we want to draw what's called side-by-side box plots, which is what it sounds like. We're going to draw 2 box plots next to each other. Okay, so for this one, we want to press menu. This time we're going to select plot properties, and then we're going to add X variable. Okay, and then we select the other one, Giants, and it graphs it for us. It's beautiful. You'll notice that I have directions right down here. Okay. Okay, so again, hover our cursor over the graph to see where the values lie, and then we're going to just graph them right next to each other. Make sure to label which box plot is which. Okay, so I'm going to graph it just as it is. The scale here that they used is 2 or 4 million, so that seems fine. Okay, so 0, 4, 8, 12, 16, 20, 24, 28, 32. Okay, so this is players' salaries in millions of dollars. Must be nice. All right, let's talk about the Dodgers. I'm going to graph them up here. Everything's pretty squished at the beginning. So Q3 is half, median is 1, and then we get to Q1, and then Q3 is 8. So it's pretty darn squished, and that's fine. So this is here-ish. Oop. Yeah, that's off, but that looks more like 2. But my little tool here won't let me do what I want to do, so that'll have to do. And then the end of the tail here is at 15. And then we're just going to graph the outliers here. One of them is at 20. You can graph them as circles. I like to use little stars. And then the other outliers, 25 and 27. Okay, there's our Dodgers. All right, and then Giants, which again, those first few numbers are really all squished together. and the median's a little bit higher. So I'm going to make that look a little bit higher, but like I mentioned, they should technically be a little bit closer down here. That's way too low. No, this should be a little bit lower. Let's see, what is it? 7.75, 18, and 19.65. Okay, yeah. All right, beautiful. Okay, so let's get into comparing the distributions. And remember, we want to try to say what we can say about that phrase, you get what you pay for. Okay, so we want to think about looking at their winning percentages. Okay, Dodgers clearly won more than the Giants. Is it worth it, right, for their teams to be paid, such different yet not that different amounts, right? All right, so let's get into the numbers. Okay, so we're going to do our Sox here. Okay, but again, we're going to not just spit out the numbers. So Sox, first S, shape. So both distributions of salaries are very clearly skewed right. And they both have outliers, which is the O. Now we do need to list the approximate values of the outliers and the fact that the Dodgers have 3 and the Giants only have 1. The Dodgers have 3 players whose salaries are outliers, and that is at 20 million, 25 million, and 27 million. I'm going to keep going down here. Compared to the Giants, who only have 1 player who's an outlier at 19.65 million. I'm referring back to the graph, of course, but that's why I don't have to look back at the numbers. So I have a piece of paper with all my numbers written on them. That's why I'm doing this, but I am, of course, looking back to my graph here to figure out the numbers. Okay, so since both graphs are skewed and have outliers, which measure of center should I use? Median. Okay, so a typical Dodger would be expected to earn, and I'm going to put M equals for median, $1.225 million, while a typical Giant would expect 1.9625 million. So a little bit higher for the Giants, but if you're thinking about in terms of player salaries, it's not that much higher. They're pretty similar. Okay. Since we're using our median, we should use our IQR as our measure of spread. Okay. The variation in the team's salaries for the Dodgers is IQR, and I did it earlier, 7.402, which is similar to the Giants IQR, which was 7.2755. I'm going to give the full decimal there. Oh, and these are both millions. The other ones. Okay, good. All right, so I did all of my SOCs. And again, I want to bring it back to the context of the problem. So what does this really say about that idea of you get what you paid for? So both teams are paid a lot, okay? The Dodgers clearly have a few players that are paid a lot more because they have those 3 outliers that are a lot more than the other players, but they also win more, right? So when we think about what that is, like clearly they're willing to pay more and clearly it's working, right? So when we think about that phrase, you get what you pay for, it seems to work in the Dodgers' favor. A little bit less in the Giants' favor, but it's not like they're like last in the league or anything like that. But, you know, in terms of the Dodgers, it definitely looks like it works. So as for the phrase, you get what you pay for, it looks like the Dodgers managers agree. And the data supports that. So even though they pay a lot, they win a lot. All right, very nice. Okay. Now, I do realize that this is a lot of writing, okay? This is just one of the things that's going to happen, especially for the first couple units that we're going to be learning. So we're going to jump ahead and do another unit that's not technically in order of the book later. And there's going to be a lot of writing for those first couple units. In general, there's more writing in stats than a quote-unquote typical math class because, like I keep saying, we're looking at real data and we're trying to make conclusions based off of that data. So we need to state our conclusions. But it's not like you're doing a 5-page essay or something like that. So keep in mind that it's totally reasonable. And this question here should take you, 10 minutes. Same thing on like an AP exam. This type of question should take you somewhere around like 5 to 10 minutes if you do it right, if you do it thoroughly. Okay, so speaking of AP exams, let's take a look at a possible FRQ, an old FRQ from 2019. Okay, so read along with me. So sizes in square feet of 20 rooms in a student residence hall at a certain university are summarized in the following histogram. Based on the histogram, write a few sentences describing the distribution of room size in the resident hall. Hey, look at that. It's like they do the same stuff that I'm teaching you. Okay, so let's put on our socks, right? Okay, so the distribution of room sizes is, what's the shape? Okay, if you said bimodal, you would be correct, which is very unusual, but I did mention it comes up every once in a while. And like I mentioned before, if it's bimodal, you can just stop there. You don't have to mention skewed left or skewed right. It's kind of skewed left here, but you can just say bimodal and that's fine. Okay. There do not appear to be any outliers. Now, in terms of like a measure of center, we do actually have some statistics on the next page. So you'll notice that they do give us our median and they do give us our mean. Since this is such a funny distribution, it's a bimodal distribution, it's not symmetric, even though it doesn't have outliers, we would probably use our median as our measure of center. So a typical room would have about the size would be about 253.5 square feet. Okay, so a typical room size would be approximately median equals, oh, that's not money, 253.5. Is that what I said? Yes. Okay. Very nice, very nice. And then measure of spread. Okay, the variation in room size would be about, and then we need to find our IQR. Okay, and if again we look at our numbers here, Q3 minus Q1. Okay, so you can do the calculations here. That's totally fine, which gives us 118 square feet. All right, there we go. So sometimes you won't have like a huge giant paragraph. Sometimes it'll be that quick. All right, so let's take a look at the next one. So this one, we're going to determine whether there are potential outliers in the data, then use our grid to sketch a box plot of room size. Okay, so it didn't appear that there were any outliers according to the histogram. Let's double check and make sure. Okay, so this is where you would need to use the outlier equations and do it by hand. So outlier equations, Q1 minus 1.5 times the IQR and Q3 plus 1.5 times the IQR. Okay, so this would be 174 minus 1.5 times 118, which we found earlier, and this would be 292 plus 1.5 times 118. So this would give us -3 square feet, and this would give us 469 square feet. So even though we don't have the data itself, we see that the maximum here is 315, which is below 469. So there's no upper outliers. And the minimum here is 134. And you can't have negative square footage for this context here. So, you know, even without looking at the minimum, we know there's no lower outliers. Okay. Oftentimes for AP exams, they want you to like be very specific. So you need to state something like, since there are no values below -6 square feet or above 269 square feet, there are no outliers. So I do want you stating, not just giving me the numbers and just saying no what, and why. Okay, so this is part of describing what you need to describe. Okay, so let's graph our box plot. So our minimum here, 134, so they have everything nicely graphed for us. So like maybe about here. Q1, 174, like maybe about here. Median, 253. Here. Q3, 292. Here. I don't know why this tool is driving me crazy. It is not doing what I wanted to do. Okay, there we go. And maximum 315. Okay. All right. So lastly on this one, what characteristic of the shape of the distribution of room size is apparent in the histogram but not in the box plot? So I've mentioned this before, but the modes, okay? The histogram shows the data is bimodal, which we can't see in the box plot. Okay, so one advantage of histograms over box plots. Nice, nice. And if you think about it, the fact that it's bimodal probably makes sense because it's probably two different types of rooms, right? Like a single room or a double room, something like that. All right, okay, getting down to the end. All right, so new example, really going more in detail on comparing our distribution, seeing what we can say based off of box plots, what we can't say. All right, so we got side-by-side box plots of random samples of fall temperatures for 3 major cities in the U.S. We're going to determine if each statement is true, false, or cannot be determined. Okay, so Cincinnati's median is the lowest of the 3 cities. If you look at the lines in the middle of our box plots, those are our medians. That is true. There are multiple outliers in the data sets. I only see one. That is false. Miami has more temperatures in their data set than LA. Now notice here, we're not told how many temperatures they took. We're just told random samples, right? So this is a cannot be determined. It could be true, it could be false. We do not know. Okay, LA's IQR is the smallest of all cities. The IQR is the box itself, right? Okay, so it looks like LA is more consistent than the other one, so that is true. Miami's data is the only box plot that is slightly skewed. Okay, so Miami, it does have a slight skew because the median's in this direction. LA is pretty symmetric, but Cincinnati, notice, is also pretty skewed. Okay, because notice the median's here and this tail's a little bit over here. So because they say slightly skewed, okay, that is false. All of Cincinnati's temperatures are lower than all of LA's temperatures. Okay, so here's Cincinnati's temperatures, here's LA's temperatures. All right, so if I'm looking at the lowest of LA, okay, that is in fact true. About 75% of Cincinnati's temperatures are below 60 degrees. Okay, so 75%, that would be my Q3. Okay, here's my Q3. It's not below 60 degrees, okay? That would be 25% is below 60 degrees because that's my Q1, so that is false. All right, I love these kind of problems. They're so fun. So let's take a look at another example. All right, 5-number summary for a data set of 300 values is 6, 30, 35, 47, and 80, okay? How many values are above 30? Okay, well, looking at the order here, this would be my Q1. So 75% of data values would be above Q1. So 0.75 times 300 would give me 225. And notice we're not given units here, so that's fine. How many values are in between 30 and 47? Well, 47, this would be my median. 35, this would be my Q3. Okay, so Q1 to Q3, that would be my middle 50%. So that would be 150, half the middle 50%. All right, last one here. Circle all the statements below that are true. Okay, there is at least one upper outlier. Well, we need to do a little math for that, right? Okay, so if I'm figuring out whether or not there's upper outliers, I would do Q3 plus 1.5 times the IQR. Well, my Q3 is 47. 1.5 times my IQR is 17. Okay, so if I am looking at that, that's going to give me 72.5. Hey, and 80 is above that. So there could be numbers in between 47 and 80 that are above 72.5. So that's why it could be at least one. It could be one or more. So that's true. Number 2, none of the values are equal to 17. Well, we don't know that. They could be. Okay, we're just given the 5-number summary. Number 3, 75 values are between 30 and 35. Okay, so that would be 25% of 300 which is 75. So that's true. There are no lower outliers. Hey, let's do the math. Q1 minus 1.5 times our IQR, which in this case would be 30 minus 1.5 times 17. Okay, that would be 4.5. Well, our lowest value here is 6, so there can't be any numbers lower than 4.5, so that's not true either. All right. Okay, couple things to watch out for. Again, don't forget to do a reality check, right? Okay, don't just let the calculator spit out numbers for you. Think about what they're talking about. Don't do numerical summaries for categorical variables. Don't do your mean of a categorical variable. That's not helpful. Don't report too many decimal places if you need to. We're going to use 3. You can use more than 3, but 3 is just fine. Don't round in the middle of a calculation. Okay, wait till the end. So when I say round to 3, that's at the end. Watch out for multiple modes or gaps, right? There was an example we did with a gap just a little bit ago. Watch out for those outliers. Make a picture. Did you graph your data? Did you really look at it? Okay. And did you answer the question? Did you explain your answer? Okay. Don't assume that whoever's reading it knows what your thinking is. You need to explain your thinking, okay? You don't always have to write paragraphs all the time. Sometimes you will need to write a lot. You don't have to all the time, okay? But make sure to explain your thinking clearly. All right, last video. I'm looking forward to a great year. Definitely finish that homework. Remember that homework is due. All 3 of those assignments are due the first day of AP Camp. So have all of those done. And also notice number 3, do save the data set for number 2 because later problems come back to it. So have that saved in your calculator so you don't have to come back to it or to re-enter it all the time. All right, I'll see you at AP Camp.